Hi everyone. Thank you very much for attending today's webinar. The title here is a time series forecasting by RapidMiner. My name is YC Lee. I'm an AI project consultant for Scientific Formosa here in Taiwan. I'm a consultant for the past 10 years. Before that, I have worked or taught in the US first and then in Taiwan for more than 20 years. The scenario that we will focus in today's tutorial is actually a challenge from a local power company about 2 years ago. Its team of mostly statisticians would like to see RapidMiner will be helping them. The training data consists of nothing but 35,000 or so hourly power consumption values from the year 2017 to 2020. The request is to predict for the forthcoming week from January 11th to January 18th. Our visit to them actually is during the first week of that year, and they just check the data later against our forecast values. Anyway, as a typical proof of concept effort to be completed in a few days, right? The customer did not ask or mention other specifics. So we just try to do our best with a given data and the requested forecast. First of all, as you know, from version 9.8 on, RapidMiner has included a rich set of time series operators as part of the system. By that I mean it is no longer just an extension from the marketplace. In this tutorial, we will deal with this problem by machine learning approach. And it is quite interesting, of course, to see how the problem can be formulated and how the data can be prepared and augmented with additional attributes. Right? Partly because we have followed this functionality of RapidMiner in time series analysis closely in the past. So we were able to respond to this request in about 2 days. And we show to the customer the result of this 192 forecasted values, right? Shown here is only just the selected hours. Anyway, it would be nice if we can show them some chart. And over there, you can see the pattern of the changes, the trend, and the customer or the domain expert can compare these changes against their own experience or understanding. We used RapidMiner's visualization tool to show these charts. And this chart, the visualization tool here in RapidMiner is of course not as comprehensive as what you would see in the commercial BI packages, but just spending a little bit effort and making some cosmetic effect, and we should be able to make the contrast or the highlights clear enough or appealing enough to our customers. Okay, so shown here is the hourly changes, right? And then in color by the selected days. Okay, usually in RapidMiner, the selected days, the color part is so-called the third dimension we add to this two-dimensional chart. And you can just change the axis from the hours to the dates. So reversely, we color the hours instead of dates, right? And for the customers or the domain expert, they can clearly see the pattern seems to be normal. For example, in the early morning hours, that consumption is low. And from weekday to weekends, and as you can see here, this chart to the right is from Monday to Monday. So what's shown for the Saturday and the Sunday clearly is the typical trend for the power consumption in Taiwan, right? Okay. When we are talking about machine learning approaches, and as all of you know, right, we not only need to show the predicted or the forecasted values, the performance metric numbers are equally important. And we don't really judge how good the model is by just looking at the predicted result, see if they kind of match our thought or not. Instead, we need to explicitly compute the performance numbers so that we can show to the customers to see what kind of model and we have come out with, right? So this is again, is for all the forecasted values. For each value, we actually have a regression model behind it. So as you can imagine, there are 192 models. So what we are showing here, again, is also just for selected dates or the hours, right? So we are showing here is the performance changes, the model performance changes at different kind of settings. So you may be able to say that in the early morning hours, the usage pattern seems to be kind of uniform. So with all the data we are given and the error number here is the relative error in percentage is as low as 3.5%. But in the peak hour, like the noon time or nap times, and might be the data will fluctuate a little bit more, so the error is gets as high as 5.5%, right? So in the same time, we can change the axis and see this performance chart from different dimensions. Okay. Now, let me get back a little bit for the background information we have here and why we prepare such a tutorial. Okay, this is actually the fourth tutorial of the set we have compiled. And we compiled them mainly from the data preparation perspectives, and we complemented them with end-to-end scenarios so as to show the pre-processing techniques, right? And what is our motivation and objective then? Basically, we all know RapidMiner is powerful and easy to use and gets quite popular these years. And but unfortunately, we continue to see that some of our customers struggle to become better at RapidMiner, right? And as we came to realize, one of the key reasons is that the creativity or the instinct that are missing. And this blocks the users from problem solving or problem formulations. By that we mean, oftentimes we are given a business problem that's vague and at a very high level. And we also don't know what attribute we can and should prepare for model training, right? So the objective here is to show all these concepts and corresponding techniques to deal with the data set transformation, and knowing the input and the output, and that create our creativity and imagination of what kind of things we can do, what kind of attributes we can actually create. And such a knowledge will come in handy whenever we are then presented with a problem, because we can come up with more alternatives for the problem formulation, and we can also create an end-to-end process on RapidMiner to finish the job. Okay. There is, however, an important reminder for these tutorials, and that is a prerequisite for these tutorials. The terms listed here should not be a stranger to you, right? We should make sure ourselves are familiar with the tool itself. And there are many operators to learn, but don't be scared that whenever we learn a particular operator, we just need to make sure we read through those help documents and make sure we understand the input, output, or the parameters. And usually it is strongly encouraged that you look into the tutorials in those helps documents and run the tutorial. Then you will see some demo, and it's clear enough to guide you through the necessary concept and the steps, right? So with some kind of comfort or the confidence dealing with all these terms here, then we are in a much better position to benefit from these tutorials. Okay, now let's get back to today's focus, right? RapidMiner has long trying very hard to make this time series analysis work faster and simple. And they do have the operators like windowing or the lag for years now. And they also have some of the transformation function and to, for example, to play around the frequency domain and or at least to smooth out the noise. So together, they can help us to do a lot of things. But the recent effort from 9.8 is that they really try to make the operators as complete and as convenient as possible. So best of all, now we can easily, okay, of course, with some practice and some learning, we can easily transform a typical time series analysis problem to a machine learning problem. And to start with, of course, then we can do the usual training steps like with rigorous validation to validate a model, right? To make sure that the model is good to when they are presented with the future data, right? But not only that, we can also combine all the other powers in the RapidMiner so we can optimize the whole process to get them more operationally ready. Okay, so that being said, that once a traditional time series problem has been transformed to a machine learning problems, be it classification or regression or other different kinds, our work will be a lot easier. For example, and then we can just jump into the auto model to take a good look and quick look at whatever model that may help our problems. All right. So now, before that, let me clarify a little bit of the confusion, if you will. Okay, people tend to use this linear regression as to say that, well, there's actually not much difference between statistical based or machine learning based approaches. And just bear with me, okay? Just look at this linear regression. You of course know what the model is trying to do, right? And for people from statistics, they might say the linear regression is a statistical model and it's aiming at minimize the square error, right? And folks from machine learning will say, oh, we train a linear regressor and obtain the same results. And almost at this point, they will say, well, no difference, and why there are always some confusion and arguments, right? Now, conceptually, if we look at this here, for statistic model, folks will be talking about inference. So there's no notion of training or test, right? And it's actually just try to assume the data is linear regressor with some random noise like Gaussian. And then we try to find this line that minimizes the error. And the objective, of course, is to characterize the relationship using a lot of statistics, the theory, or the implementation we have done before, right? Now, as for machine learning, first it comes to mind is that we have to split the data, or at least some kind of way is to train with a set of data and then test with the remaining part so that we can ensure the model will be consistent and will be able to take on the challenge from future observations, right? So it's a training and test is a clear notion for machine learning. And now, if this is not enough, let's quickly go through the scope of these two approaches. First, you will see that when there's a single input and statistical approach, which is treated as simple linear regression problems, usually it just calculate some statistics such as means or standard deviation or whatever, and it's just good enough to come out with the model, right? And then when there are a little bit more input or whatever, then you do things like some would say it's ordinary least squares. And here we are minimizing the sum of the square residuals, right? And what's unique is that with today's computing power, the data can be considered, the whole data set can be considered matrix. So we use linear algebra for these metric operations to estimate the coefficients, right? All data should be available for traverse, so the memory should be large enough to accommodate this matrix. On the other hand, from the machine learning approach, we first think about the gradient descent approach, right? And this kind of work, I actually start with the assignment of some random values to this coefficient, and then we try to optimize the objective, that is to get the minimized sum of the square errors. Now, a learning rate is always used here as a scaling factor, and that would decide how much update we should do onto this coefficient moving toward the minimization of the error, right? And then repeat this process until the objective can no longer be improved. And now, after gradient descent, some folks will say that we not only want to minimize the error, we also try to reduce the complexity of the model. So here comes something called L1 or L2 regularization. You have heard about that, right? Simply put, that L1 is to minimize the absolute sum of the coefficient, while L2 is to minimize the squared absolute sum of the coefficient. And this particular approach here is effective when there's a collinearity in the input values. Okay, let's stop here and hope that at least clarify a little bit of confusion people will talk about, and then we are in a better position to explain to folks that these two approaches are not right. So the outline for today's talk is that for the first part, we'll try to go quickly throughout this the operators provided by RapidMiner. RapidMiner does have a lot of useful operators for those who are familiar with the statistic approaches, right? By that I'm saying when you look at a particular model, you know what the parameter means, and you will try to find a good combination of parameters. So for the part one, we'll go through that and then quickly move into a machine learning based type of approach. And here, with both approaches, we will also see the operators such as forecast validation and working with the optimization parameter operator and then apply forecast. This usually started trying to introduce some of the performance measures for the time series problem. Now, once that's all clear, we move to the part two, and that's when we come back to this data set we first presented with, right? And we will show a complete end-to-end process, that is to prepare the data and then try and validate them and then do the final forecast. So for the same data, we'll split it out for training purpose, for validation purpose, and for forecasting, right? And of course, there's some pre-processing step that we have to be careful about. But some of you may start questioning that we are given a simple list of time series data, right? This is a stream of 35,000 data. Then how come I'm calling this about like a multivariate, right? And also multi-step. Multi-step is clear because we are forecasting 24 hours for 8 days, and that is 192 values to forecast. So there is a multi labels we're dealing with, if you will, right? And then in terms of multivariate, and if you're from the School of Statistics, you will know multivariate is is quite animal compared to the univariate, because the formulation or the statistic involved will be a lot more rigorous than that uni case, right? But this may not be a same story if we are in the machine learning type, right? Thinking about machine learning problem when we're trying to predict on an observation where we have many attributes for that observation. So some of the observation can be the value itself, and other aspect of their observation can be external data or whatever. This is typical in machine learning approach. So for example, we could have just go out to get the weather information during that period and to play with, and that will form another set of a subset of observation, right? But in here, we did not really go out, but we can actually try to compute some load average, for example, the weekly load average or monthly or daily, and use them and even put them as a window in approach, and put them, so for example, for one observation, I like to see the previous 3 weeks average or the daily average from 10 days ago until yesterday, right? Things like this. So you can easily add it up and to make it a multi-attribute observation, if you will. Okay. So now let's start with part one first, and we will just go through some of this operator quickly. You can easily practice them. So my main purpose is just to tell you what's available in RapidMiner. So usually we try to split the time series data into 3 components, right? And easily you can use the STO decomposition, and that has some component, and then repeatedly calculate to come out. And the parameter we use, for example, seasonality, usually we set it as a number of months in a year, right? And then the seasonal width is just a much larger window so that we can kind of catch the seasonal changes, right? So for this, if you're not that clear, just quickly, the black is the data at the time series data, and the blue line is the trend. And down there, the green part is the seasonal data, and the yellow is the remaining things. Quickly for ARIMA and exponential smoothing, you also call it the whole winters, right? So in RapidMiner, we can have this simple process, like I retrieve the data and run ARIMA. Of course, when you run ARIMA, you should be able to put in the values for the 3 parameters, this P, D, Q down there, right? And then after you have the model, you can apply the forecast, right? So quickly, you see the example. Or you may not like to see the result here, and you may even say that I'm not giving ARIMA a fair justice, but excuse me for that. But anyway, we were just showing what we can do, and if you are interested in play with that more, and you should be able to learn to verify a little bit better. And in terms of this exponential smoothing, once we can use a similar process here, just replace the ARIMA operator with whole winters. And here we also have 3 parameters, alpha, beta, gamma, right? And run it, and it sounds like we get some forecast more to our like. Okay. Again, these are all just subjective feelings, and we need to compute the performance in order to say objectively whether the model is better or not. Again, let's not argue about them. Here, let's focus on the selection of the parameters, right? Usually we would think that can I run through some optimization automatically and ask this set up to iterate through possible combination of the parameters. And for all these different combinations, we try to calculate the performance so that we can determine whatever our configuration does the best job, right? So in RapidMiner, this is typical. We call this optimized parameters. We can then set it up what range or what kind of increment we like to have for each parameter we selected to optimize, right? And inside there, I can have something. This is a new operator you may not have seen. Right? There's a forecast validations. So the outskirt will prepare all this. Will prepare this various configuration we talk about, and then for each configuration, they will kick off the specific job that will be described inside this operator. So as now you can see, it's typical to our cross-validation type of setup. To the left is the model creation, and sometimes it's training, but for this whole winters, they have the algorithm to come up with the model, and then to the right will be the performance measure, right? That the forecast validation also does another thing, that is to let you choose what kind of validation scheme you like to have. For example, here is something called sliding window validation, right? They kind of shift from, say, the first iteration, take the first 7 records, 4 of them for model creation, 3 of them for the performance measure. And then for the next iteration, they just move forward by 2 timestamps and have another set of data to calculate performance. So quickly, you can see that's how the optimization has performed. And we come out to this, the best configuration here. The parameter varies like that. And you can see to the very right, this root mean square, that is what we performance against, right? So 17.226 is the best value we can achieve at. Okay, and so that is the result. And the result is actually similar to what we had previously. But anyway, these are the typical things that you can play with RapidMiner a little bit beyond what we would run a program or a Python or R to do. And I think if you're familiar with RapidMiner and still want to play with the traditional statistical approach, you can also benefit from RapidMiner's facilities and all these operators. So that's just the main thing I would. Now, up to this point, we can quickly review a little bit what operators we have talked about, right? And this is a snapshot I got when they first have 9.8001 and then make the stronger announcement for the complete set of time series operators. So you see that we run the STO decomposition, and then to the right, we apply the forecast, which you had the ARIMA and the whole winters operators. Right, and then down there, we also can do the validations like forecast validation, the composite operators, and inside it we choose the sliding window validation. Now, there's also things in this yellow colors, right? It's the windowing and the lagging. That's usually try to put together some previous values just right next to the current value, so that we make a training record out of single value. And I should show this later graphically, then you can easily understand the idea, right? And of course, by the time we're talking about this forecast, there's a multiple things. So we should also quickly show this multiple horizon forecast and how the multiple horizon performance operator can be. Okay, now this is probably the most important conceptual twist we should have, or the adjustment, moving from a time series data and time series analysis problem into a machine learning problem. Okay, and as you see that earlier when we talked about sliding window validation, we did not really use the whole set of time series data. We actually just pick up some of the data to do the training, and then the remaining few for the prediction as a test. So now you see this, the double circle with yellow will be the very last observation we have, right? So imagine that I just want to train something, right, using current value and the previous 4 values. And that will be one of the training record I try to create. And using this idea, we can then start in collecting more training samples, right? For example, I use yesterday's data as a very last observation and I put together its previous 4 days. Then I form another training record. Of course, I need to shift accordingly that the value try to predict, right? Of course, we need to know all these future values for training purposes, right? And so here is how they come out. And if you just label the current value as x0, be it today's value or yesterday's value, and then the previous days by x minus 4, x minus 3, and lighten them up, you would have a training set like what we shown here, right? Now, if you're still having some doubt, you can look at, for example, this x minus 4 days that say it is December 27th, right? December 27th observation. And for that same value, what kind of role they play in different sample record, then that would be this, right? So for if you set a particular day as a very last day, and the previous day will be positions like that. And so are the predictive values. So in some sense, if we can make this conceptual twist, we can start collecting part of the strings and to form a training record. And once we have a table like this, we are very much ready to do the machine learning type of approach. Okay, so just quickly show how we can prepare this data. See, here is a given data. It's a simple timestamp column and the value column. And say if you want to prepare a training record, right, the X would include all the past 20 values, and the Y will be the next 5 values. So using the windowing operation, we try to get the data like this. Here I only show the 2 future columns because of space, right? But quickly you can see that if you consider the original data is a circular column, and now you turn it clockwise by 1 unit, then you get 1 timestamp shift, right? Then you have the second column. So look at this +1, the next day, the value, the predictive value we should have. The actual value we should have, so we later can train our model for. And the next column +2 will be just a clockwise shift upwards, right? Oh, in time-wise should be backwards, right? Am I right? Yeah. Time-wise meaning the current value become the previous value, right? If you talk about the next day's forecast. Now, for the past date, you can see very much similar things. -19 or -18. By the way, these attribute names are all created by system. So you see that same value that's slanted across the table. Okay, so now we are in a good position to use whatever training type of flow we are familiar with. First of all, we will do this windowing like what we just described, right? So usually you set up the window size as 20 and also set the horizon size as 5, right? And once we run it, we will come out with the data like we shown earlier. Of course, this case, we should have 5 columns in yellow as our labels, and then 20 columns in white, that's our observation. So we split them as typically done, and then now we get to this training operator. We used to see something like, a different algorithm for training a single label type of operator, right? But here, because we are forecasting a number of different labels, and the system will do this for us. So this particular operators, again, in the outskirt, they will set up the iteration to iteratively forecast for each value we are interested in. Inside the box, of course, we can call whatever learning algorithm we like to call, right? And because in this case, once inside this iteration, we have nothing but a number of attributes to predict on a single y value. Okay, that makes sense? So quickly, once we apply, we can see the value here. Now I'm showing you different chart here because we are dealing with 5 forecast values. So on the top, you will see that this is the next year forecast for GOM approach. And green one will be the predicted number, and the blue one is the actual values. And down there, you will see the 5th year forecast. Okay, so compare these 2 years, look like the forecasting or the trend are quite different, right? And then we can use a different algorithm. Here we use GBT, gradient boosted tree, and they have a different kind of forecasted values. Now, you probably start making some judgment, whichever is good to you or not. But again, without the explicit performance number, we are not really in a good position to objectively tell whether the model is better, one is better than the other one. Okay, so what we need to do is that to follow up the previous process with a performance measure, right? Again, here we're dealing with multiple forecast values, so we have some corresponding operators called multi-horizon performance. And the outskirt of this, the composite operator, again, is handling all these iterations and spit out the individual results, right? And inside there, it will be nothing but the performance we usually call, right? So once we have this performance number shooting out a lot of performance records, now we can just use that simple approach to combine them so that we can do a simple comparison. So here I am. I ran the GBT and run the GOM, and I can put together and choosing the attribute I like to generate this chart, right? So the y-axis is those forecast year, right? 1, 2, 3, 4, 5, and the y is the errors, the root mean square error here we use, and so the lower, of course, the performance is better. And so look like that GBT is not as good as GOM for this particular try here. And then same thing for absolute error and relative error. Okay. Again, I'm just showing that quickly, conceptually, and the real implementation, we can run a simple example here like this. And on RapidMiner, we can quickly come to some good objective judgment on how good the model is. And that is typical, and it is just like when we are doing for typical machine learning type of problems, right? So here you can sense that instead of R or Python or whatever other kind of programming approaches, on RapidMiner we can deal with a machine learning problem just as easy as others, right? Oh, by as easy as others, I mean as easy as other kind of problems on RapidMiner platform. And personally, definitely, they are all easier than programming efforts, right? Okay, I'm sorry. So let's pause a little bit here, and must give some acknowledgement and credit to the people behind these features. And Dr. Fabian Tam is in Germany, I think, in their research headquarters of the RapidMiner. And he has been the key person behind this time series operator set. So if you are interested, and actually I would strongly encourage you to watch this particular video, okay, to learn a little bit of the insight from him. And usually you can also check the courses available in RapidMiner, and they are in a all the courses are split into short videos. Each video covers a critical concept, and you can just quickly pick them, read it, and the system will recommend you to watch others, and quickly you will be able to learn some of this concept and handle things much easier. Now let's move to the part 2. This is the data we shown earlier. Just a quick notice here is that to the top right, sorry that the header row is in Chinese, right? But the second attribute indicates the date, and then the next column is the time, right? So for example, for the date, 106-0101 is a local format, or the customer's preferred format. So we have to, inside RapidMiner, we have to transform them to year 2017, January 1st. And for the next column, that will be the hour, minute, right? So it's the first hour of the day, and etc. Okay, and our target is to forecast some values and with some. First of all, we need to clean the data, right? And also mentioned that whenever we are given a data set, they have a lot of local arrangement in there. For example, we just talk about the date format. That is their company's decision to do that way. Now here also for the missing values, some company may just choose to stick it in with a 0. I think there may be no harm if they can interpret it. But when we use this 0 value directly into the machine learning training process, and you know it is just not good, right? So we have to identify them by talking to the domain customers. Of course, you might first detect them when you are trying to do some exploration, but you always can double check with the customer's domain expert. So assuming that we find these 4 values, that's what I found. I'm not assuming, right? And I remove them from the data set. Now, let's look at these additional attributes, right? First of all, we manipulate the datetime column to get a correct datetime stamp. So now it's a datetime inside RapidMiner now. And the move on is that we might be interested in saying, if I use the first record as a reference, then I look at another record, and I would like to ask what year number is that second record, what the month number is this second record from the very first record, right? The week number, day number, etc. And after that, for power consumption, things that is so much depending on the seasons or whatever. So we may like to just say, looking at the record, I would like to ask whether what month this is, what week this is, or the day. And down there, we start trying to collect some of these aggregates at different granularity level. For example, I like to find out the average load of the month, average load of the week, right? And it just consciously or whatever, we think these attributes might be helpful to us if we can somehow catch some of the historical patterns, and maybe they will be useful for or beef up our data set for training purpose. But again, these are just candidates, right? And with RapidMiner, all the convenience, we can easily compute them, add them, and modify them, and it's to see how good that is. And that's where the fun is, and the convenience you get from the RapidMiner. So if we just try to visualize this data first, and say I just follow the previous slide, I create some attribute. The first one, I use generate attribute operator to convert the date, right? So now I have a good YYYYM type of format. And the second this is actually directly from the previous table I just shown. I use some of this data manipulation functions in RapidMiner to calculate hour of day, date of month, not calculate, to extract out, right? And some of them probably need some computation, but anyway, as you can see, these are the logic to derive those attributes. Now, we are not talking about into this training process yet. I'm still at the visualization tool, right? So very usefully, really, this is a fairly useful things. On the visualization, say, I just want to look at whatever data set I have. I want to calculate the mean, the average, right? So if I set the axis as the day number, remember 0 up until 1427, the number of days for every record. So for every day, we can have 24 values, right? So the visualization tool will simply just calculate the average of those 24 values for that particular day. Now, move down, we change the day number into week number. And in no time system would show us some of the pattern like this, right? The curve looks simpler because now you have, for every week, you have what, 24 by 7 is 168 points to calculate the average. So move down, you can see the pattern or the trend, and at the end you see, well, for over those years, indeed, the power consumption just moved up on the yearly average. So now if we want to get a little bit more exercise or to see a little bit better, and maybe we will prepare the chart like this so we can talk to the customers, right? So you look at this saying, well, we will just, again, computing those averages based on whatever axis values or the grouping value we are trying to color them below, right? So you see this, all the dot are the average values. And to the left is hour of day, and each curve is corresponding to the month of the year. And to the right is just axis changed. So you can see that the lunchtime and noon time by the different month or the different week of day, that definitely shows some differences, right? So for example, at the right, you would expect during weekdays and during weekends, this pattern will be quite different. And so at least we are looking at the data and in a corrective way, right? So things, if I like to see from Monday to Monday and how this average changed for different kind of setting, and you can see them clearly. And then, so for the visualization, usually we have 2 dimensions, and then we add a third dimension by coloring, right, by grouping. And then for the numbers, we can try to see the maximum standard deviation or the average value, so that they will give us some feel. And when we talk to the customer or try to help us to look further into the problem, then we have a better sense of the data. That's important always when we try to do some machine learning problems, right? So now back to this picture here. It's very much the same setting. Now you can, if you follow what I just talked about, we can say, I'm going to add a number of attributes, say U and V and W here. And they were created by me, either by aggregation or some other different kind of schemes, right? And we probably change to take a short window and change that to frequency domain and take some characteristic out of it. So graphically, it's like I'm now going to do the forecast. My observation has 3 parts. The first part is the original signal, x minus 4 up to x0. And the second part is w0, just some other value up to this point. And the third component will be v minus 2 to v0. So this is quite natural and straightforward in the approach we use it. So like earlier, we have this setting, right? And I simply collect or derive these new attributes, and that's where we beef up our training model, and with hopefully more informative type of observation for us to train the prediction for. So now, get to this implementation part. We may not have time to go very detailed into this, but I think you can look at this and very much guess what we are doing, right? And I will just quickly go through them. I split them into 4 steps. The first one is actually to set up the stage. I use some of the macro to prepare the data, right? And one thing important, I will talk about that later. But the second step is to do the data preparation. And the third step is to do the training and the validation. And the fourth step is to do the real forecasting. Remember, when we have given this data and do this, that time, the forecast period is not up yet. So we are forecast something we really don't know, right? The first step here is I use some macro to narrow down the problem so that I can have a better understanding, partially and incrementally try to build up the whole process. Say I here just want to look at the 23rd hours, right? And I have 8 days to forecast. And the model 1, 2, 3, just I designate them for the specific algorithm I use, right? And I need to use this variable, and so that I can name the output properly, the model or the performance number. So later I can collect all the data together, and then I can show graphically, right? So the metrics I would like to look into is relative errors and percentage, as you see earlier. So here I add some parameters like this is the window size. I want to look at all the values, right? It's back to the previous 14 days, right? Or then average week average, I like to look into the previous 4 weeks, right? Now the last one, offset date, is kind of a little bit tricky. Remember that the last observation is December 31st, and the first prediction date is 11th. So there's a gap of 10 days. That's what we call the offset date, right? We have to be careful about that, otherwise we cannot prepare the data well. So another things to be cautious about is that we are taking the whole set, right, including the future records, and so that we can do all this computation. For the future record, of course, we don't have values, but we do have the timestamps, right? So they are still a record. And the RapidMiner, when they try to prepare all the windowing, all these processings, they will look at the values. And if, for example, I'm preparing for training data, and if they don't have the actual value for the performance variation, they won't be included. And so we have to make sure this whole complete set is really exactly what we have, right? And then move on, we do the data pre-processing, and then try to do some aggregations. And the date is no problem. I think you can easily find out what they do, right? But for the aggregation here, we just play with the windowing, and sometimes we aggregate, or further down we do the windowing to put the history of the aggregates. Remember the case where we like to include all the 3 weeks week average as observation. So that's where we first do the aggregates on the specific day, and then try to do the windowing to repeat. Remember that this week average will show up in every records, right? So that's how we create. And then now move to the third stage. That's where we do the training and the validation. So you do it first, do some split. Here's 80-20 split, but be caution that for time series type of problem, when we do split, we need to split them by chronological order, right? You will never try to predict the past by the future value. Once you do that, your model is no use at all, right? And that you can find out the reason why if you give some thought. Anyway, here we use what we earlier talked about, multiple horizon forecast, and apply the model, and then we have the multi-horizon performance, and try to collect all the performance value at the end. So up to this point, we are very much done with the training and the validation. So what we have, of course, we store the models, right? So as you see that in the center here, we output the model to save us as a real forecast, right? We are at the 4 steps. Now, this is very important, right? Because for the observation we have to forecast in the future, if you were doing the original data set as a typical time series analysis, for the observation, you have nothing but the date, right? But the date's timestamp. But in our approach, here the observation includes not only the previous value, but also the additional attribute we try to create, correct? So we have to get them ready as well in step 2. So what you are seeing here is, first, we try to predict all these 8 days, right? And then, of course, they don't know because we are doing the real forecast here, right? And the last day we look at is December 31st. But we need to know what day of the week, what months of the year. These all need to be derived and make them as explicit attributes. Then further on, you try to include, for example, here, previous 3 weeks averages. So these need to be computed and attached here as observation. And further on, you want to include all the previous 14 days, right? So that's what you have. Now, this is what we got to get them ready before we can send into a prime model. And then once you have them applied, then you come up with the forecast value and then just store them for the final output. This is clear. And once I run it, remember I just do it more incrementally. So as a result, in that folder, I get all this different performance number for each individual hour. But still, for each individual hour, I have 8 forecast values, and that is 8 models. So I do have 8 set of performance matrix number. Here you see that we collect the root mean square error, absolute error, and the relative error. And then the fourth record is for another forecast day, right? So I just go through this process and put together. These are something that it's no big deal, but you like to practice a little bit so that you always can put together the result from various runs, right? If you first start with a proper naming, and then somewhere you go through this selection criteria to collect whatever subset you like to look at. So in a way here, for example, I can quickly pull out for the different hours and their relative error, right? As you can see, they are all between like 3% to 5% or something like that. So now, this I hope to go quickly, but it is important. When we try to do something to prepare a model, but our whole problem is actually much more involved. Here we want to say you want to have the operational model that will be good to go. And always they will take a 10 days gap and to predict the next 8 days for every hour, right? So for example, today is end of the year and I try to do that. So can I have the model whole mechanized? That means that will automatically trigger it and it will run and come out with all the result. And this is what I try to do. And for those who who are not so familiar with this, this is called more of this utilities. So use the set macro or the looping operators a lot. And then a lot of the time you also do some data format transformation, right? And at the end you can collect either the forecast values or the performance. So very much, as you can see, that I go through the steps and try to put together the earlier sub-process into these like daytime pre-process. The loop. Inside that loop, as I shown here, will be whatever model creation we have. And then of course, inside there, we should have some good data preparation to start with, right? And then the prediction at the end is to collect all these predicted results, right? Okay, and then the very last step is I also combine the performance data and so that I can play them with. Now the data sometimes comes in just different format. For example, they might appear in the whole column and you need to flatten them up. So pivoting the operator is also useful. It takes some understanding, but it is worthwhile. So anyway, that's where we can quickly come up with this whole 992 values, right? And otherwise I would have type or manually spend a lot of time to run all these 192 values, right? So what I'm trying to show is that on RapidMiner, and you spend a little bit effort, make sure you are familiar with all these utility functions and the looping things and the data transformation. You can easily put a similarly complicated process together in just one hit of the run, and you come up with all the data. And then you take the data into your visualization place and properly select the attributes as an X or as a Y axis, and then do some grouping and color them and then calculate the aggregates or whatever. So that's how I get all this load chart, right? Performance chart like I shown earlier. Okay. Now this is very much the story, and I could have finished them here, but I just want to quickly show you this can be a challenge from others, right? Customers would ask you that, well, I learned about the deep learning. I know the latest things. They have all this, not just convolution 1D, but also LSTM or whatever. Now, it's fine that if you're interested, you can run it, right? And there are examples, and you can learn to how to set it up. But of course, you can imagine that if you want to prepare the data set as rich as what we are showing there, then you need to be good at the programming, right? And then where you play the indexes to do the indices to do the windowing. But anyway, at the end, you like to see if you get the reasonable good conversions and a good performance. I'm not talking about performance of a computation, but the performance of the model, right? And but there are also other people saying I can do all this traditional algorithm rather well in Python. So you can try, because for typical things like linear regress or decision tree, they have a upgrade version that can handle multiple label. And for GBR, this graded boosted regressors, they don't have immediately the operator for multi-label, but you can also find the wrapper to wrap it around. So what we like to do is that we'll just create some program to do this, and then collect the performance number and put together to do the comparison. So I will fly through the effort I put here. To me, it's meaningful. Okay, I also write Python. I don't write R that often, but I read Python, and one of the particular interests is always to run through Python to feel a little bit about the trouble that typical user will go through in comparison to the RapidMiner. Okay, so you see this. I start with this Python including all the libraries. Remember, we are going to try both deep learning approaches and then the traditional models. So I also put the different configuration to be associated with the different algorithm run with. I give here, try it out to see if I only use the signal itself, or I would use a signal plus day average, or signal plus week average, or I will have all them together. So I actually just as a program to run a lot of things, right? And then for the derived attributes, something as simple as to see what is the number of year, what is number of week, or the whatever. But some of them gets a little bit more complicated. You need to do aggregation, right? So this is where the programming gets a little bit touchy, and you have to make sure that you know how to do them, and hopefully you don't run into some of the careless bugs, right? And now here is where equivalent to the windowing, and we play with the indices, move around the indices up or back or down, something like that. And then finally is just remember I have set the configuration for different kind of combinations. Sometimes I choose only the signal only, or sometimes I choose all the attributes. But as you know, I just run the loop and then try to see which one is best, right? And this is the final wrapper. We do the forecast, and whatever we can plot on the by this program, I plot them, and then I also run this simple MLP algorithm rather than the newer LSTM and Conv1D, right? So Conv1D here, I include this algorithm here, and remember is that you can look into the examples in the internet. Those are all simple. So what's behind is how do you set up the problem, prepare the attributes you like to have, and then following them. But of course, the tricky part here is to set up those parameters, because if we don't really set it up well, the learning process don't even get converged, right? So anyway, I run all these algorithms and necessary groups. First, I will show you that when I run the MLP algorithm, and just for the first hour, and it looks fine. The train and the validation, they can converge fairly well, right? Now, for Conv1D, it start giving me a hard time when the validation is always stay up, and that 40 is the relative error, right? It is in Python is called what? Average, what? Mean of absolute percentage error, right? So it is not right. And for LSTM, seems like they follow well. The validation and the training is rather consistent. But the relative error, or what you call mean absolute percentage error, is really way too high. We are talking about 3 to 5%. Here, I'm dealing with a number in double digit, or even as high as 80. Okay, maybe I did not spend enough time to tune up, to shore up these two approaches, but believe me, I gave them a lot of time, and it's just not worth it. And for MLP, it's barely acceptable, right? Even though it's as about with a bit more than the 5%. Now, so you can also quickly see that either L1 or L2 doesn't make too much difference in this problem set, right? And then the decision tree is similar to this k-nearest neighborhood. So at the end, I run successfully for the LR and the DST, and then also GBR with wrapper and the MLP. So I'll put them together, and then finally I have this chart. Okay, and the black one is a MLP one, right? And if you recall what we shown earlier by the approach, we were able to get below 3.5 and no more than 5 point something, right? But here, all these things I just run, they are closer, but still a little bit above what we had. But it's not really the key point here, because we can always try to tune and sharpen it up and try to play more, right? Its good part is that either you have a RapidMiner process or you have a Python programs ready there, and you just keep on running that as long as you have time and you have the computation power to do that. But the point is really that conceptually we did it on the RapidMiner, and the things are much more easily tractable or debuggable. So we were able to come up with the results, and meanwhile I can explain to my customer the process I followed through. Might be they will take a little bit of time, but at least I have a good documentation and the flow of the task I'm doing. And if I were to show the whole Python program to my customers, I think I would just blow them away, right? If you so happen to run into some customer who are very good at programming, then you two probably sit down talking and ignoring all the other audience. And when you talk, because people don't really program as a whole picture that well, so you too may also waste a lot of time trying to digging out or guessing what the program tried to do. Okay, now that's my thought. Okay, hopefully that you can think about it and see whether I'm making good sense or not. So now here's the takeaway. The part one, we went through some of these operators, right? We went through them quick, but they are really useful. So we should try to familiarize ourselves with these operators. Then to the second part, I do this multivariate, multi-step, complete scenario doing that. And of course, I use additional attributes mostly to beef up those derived attributes. For example, it's showing here in the blue is that process the windows and extract aggregates, extract mode, or extract peaks, whatever this kind of operation. We talk about these operations in more detail in tutorial 2. So I thought in this tutorial 4 we just go quicker. But you're welcome to look at the tutorial 2, or just to, again, it's like always, you learn from the RapidMiner by looking into the examples, looking at the operators tutorial sessions. Okay, thank you very much. This is rather long. Hopefully I did not extend too much of the time given to me. And quickly, it is SFI, Scientific Formosa, here is the RapidMiner representative in Taiwan since 2017. And we provide the local support as well as professional services. And the company has presented many popular software tools, more than 30 years now, and help a lot of customers to go through their digital transformation initiatives. Okay, thank you very much for attending. Bye-bye now.